Okay, once we get into bases, they will for the most part be treated the same way as the acids do, strong versus weak, except now for the equilibrium we have Kb values, and then we're not calculating hydrogen, we're calculating hydroxide, so we get POHs. Calculate the pH of a solution made by putting 4.63 grams of lithium hydroxide into water. So 4.63 grams, we need a molarity. So the molar mass of lithium hydroxide, 23.95 grams per 1 mole, comes out to 0.1933 moles. And we've got 400 milliliters, so 0.4 liters. We get a molarity of 0.483. Okay, now that's a hydroxide here. So negative log of 0.483 is going to give me a POH. Which will be 0.316. So the extra step, since that is a POH, is to get a pH. At the very end, we just say, hey, 14 minus that, the pH is 13.68. Common sense test will help you here. If you have a base, the pH needs to be above 12. So that 0.316 can't be the answer. That is a POH. Calculate the pH of a 0.04 molar barium hydroxide solution, which looks to be the same problem. Negative log of that number should be the hydroxide, except for this pesky little 2 from chapter 4. Because we know that when barium hydroxide dissociates, we do get 1 barium, but we get 2 hydroxides. So since it dissociates completely, let's just kind of say, hey, this 0.400, this is a stoichiometry chart, not equilibrium. We know that this will be 0, and we're going to get 1 barium, but we're going to get 2 hydroxides here. So this X here, 0.04, is going to give me 0.04 barium, but it's going to give me 0.08 hydroxide. And this is the number that we need the POH of. So the POH is going to be the negative log of that number, negative log of 0.08. It's going to be 1.10, which will give me a pH. 14 minus that, 12.90. Hydroxides are tricky. Acids don't do this, but you have a lot of hydroxides that come with multiple hydroxide ions. So watch out for dissociation of hydroxides. Here's just a list of your common weak bases. We've talked about this before, but it's a lot of them are nitrogenous bases. They have ammonia, amine groups that have the same structural properties of ammonia. Pyridines have these rings with, again, nitrogen on it, and those nitrogens are very good at accepting hydrogens, which is what classifies them as a base. So calculate the pH of a 0.35 molar of methylamine. And since this is not a hydroxide, we know it's an equilibrium, and we also know it's an equilibrium because they give us a Kb, and that Kb is a clue that it's a base. So there's a lot of clues here. The equations, though, is the new part for bases. CH3NH2. We have to add water here. We had an option with the acids, and it's usually easier to leave it out. But with bases, we don't have a choice. This is going to steal a hydrogen, because that's a base. It has to steal it from somewhere. It's the it's the water. So if we get CH3NH3 plus, how did that hydrogen get over there? Well, it took it from the water and left us hydroxide. And this is the first time you can see why this thing is basic. When you put it in water, it does not contain a hydroxide, but it makes hydroxide from the water. So that's important. Once you get that, this is just a weak base equilibrium, just like the acid equilibrium. This is 0.35 minus X. We don't care about the water, even though it has to be there for the balanced equation. It's not in the race chart. These are 0 plus X, X, and 0.35 minus X. So KB this time is going to be x squared over 0.35 minus x. X will come out to be 0.0122, and that is the hydroxide. Okay, so a negative log of that number is my POH. Hydroxides give you POHs, 1.91. 14 minus 1.91 will give me the pH, 12.09. Just like acids, we have the follow-up question. What is the percent ionization? Well, I started with a 0.35 molar solution, and we had 0.0122 moles come off of it, part to whole times 100. Will give me, this is a 3.49% solution. And just like acids, they could give you the percentages to go backwards and figure out X, and then you could solve for the Ka. They gave us the Ka in this case. Calculate the pH of a 1 times 10 to the negative 11th molar solution of NaOH. So first thing here is there's only one hydroxide. That's a good thing. Negative log of this number will give me a POH of 11 and a pH of 3, which is not the answer because this is too dilute. We've talked about this with the acids. This is too dilute. You cannot have a base with a pH of 3. It does not cross this water threshold. This is a neutral solution with a pH of 7. Unless you have enough sodium hydroxide to get above this threshold, you cannot change the pH. It's very similar if you were to take a drop of strong base and put it in the ocean, you did not change the pH of the ocean because it's too dilute. You need concentration, you need a lot of it to change the pH, and the threshold there is neutral water. Hydroxide is 1 times 10 to the negative 7th. And then the bases are pretty much that easy. You could have two strong bases that you'd have to add all the hydroxides together, just like we did with acids. You could have a strong base and a weak base, where you only take the strong one into consideration, or you could have two weak bases and you just take the stronger one into consideration. So all of those things can come back up. Changing gears a little bit, now that we've looked at a little bit of acids and bases, we get this neutralization reaction, which is kind of a preview of 15, and this will be the first time we're looking at mixing an acid and a base together mathematically. So right now we're only going to do this with strong acids and strong bases. The weak ones will complicate things later on. So what is the pH of a solution formed with 20 milliliters of 0.5 molar nitric acid and 25 milliliters of sodium hydroxide? If I wrote my whole balanced equation, sodium hydroxide plus nitric acid make water and salt. So this one's sodium nitrate. This is a stoichiometry reactions. If you need to write down, all neutralization is stoichiometry. However, since these are all aqueous, it means we actually have spectators. The only part that we want are the base and the acid making water. That's the net ionic part, because this water is a liquid. That's new. The sodium and the nitrate are spectators. And there are volume changes. So this is going to come back up again. Now we reviewed this for the semester exam, so it's going to come in handy. We want to know how many moles of everything we have, because we have volume changes. These are initial moles. We want all 4 ions. So sodium is going to be the 25 milliliters of 0.55 molar. That's going to be 0.01375 moles, which will be the same as the hydroxide, 0.01375. The hydrogen from the nitric acid will be 0.01375. 0, 1. And that comes from 20 milliliters of a 0.5 molar solution, and that will be the same as the nitrate, 0.01 moles. Now, spectators are going to be the same as they always are. It's going to be the sodium and then the nitrate. So sodium, we want the molarity here, is going to be 0.01375 moles. Since it's not reacting, those moles stayed the same, but now I have a total volume of 45 milliliters, 0.045. So the molarity of my sodium is going to be 0.31. Okay, because it says, what is the concentration of everything in the solution? The spectators are not reacting. They are being diluted. So the nitrate is 0.01 moles, 45 milliliters. Okay, so our volume total, it's good to keep track of, was 45 milliliters. That gives us a nitrate of 0.22. Okay, so those aren't reacting. What is reacting is my hydrogen and my hydroxide, which will always be the case with acids and bases. Hydrogen, it's a 1-to-1 ratio. Hydrogen moves off the acid onto the base. We get rid of the spectators. Hydrogen plus hydroxide make water. Now, we don't care about the water, but this is any acid-base reaction. This is a stoichiometry problem. They will always be stoichiometry problems. My hydrogen is 0.01. My hydroxide is 0.01375. And since these are all going to be 1-to-1 ratios, it's really easy to see what the X value is. It's the smallest number. The hydrogen is going to 0. X is 0.01, which leaves me with 0.00375 moles of hydroxide. All right. If I have 0.00375 moles of hydroxide, I still have the same volume, 0.045 liters, and we get a hydroxide molarity of 0.083. Since that's a hydroxide, we can get a pOH of 1.08. 14 minus that gives me a pH of 12.92. All right. So here we have again, chapter 4. We have to keep track of volume changes, dilutions, spectators, net ionic equations, and stoichiometry. Except this time we're not making a precipitate, we're making liquid water, which actually simplifies that part of the problem. I don't have to worry about the products. What makes it harder is my reactants are important. Which one is limiting in excess? I have excess hydroxide, which affects the pH, makes it basic. So I need a pOH to get a pH. If I had excess hydrogen, that would just give me a pH directly. But I have to keep track of all the spectators, all dissociated, or I'm sorry, all 4 ions dissociated, so I can sort them out into spectators and net ionic equation reactors. Do all of this work here in moles to see how much you have left over to get a pH. We're going to do a lot more of this in chapter 15. These are just strong acids and bases. Once we add the weak ones, it actually gets a little bit harder too. Hopefully that was a good review and you were able to follow along with a strong acid-base neutralization reaction.